In this lesson, we are going to continue our study of sampling distributions. So here's a quick review for the sampling distribution of one sample mean. The sampling distribution of the sample mean is approximately normal in the following situations. If the population of measurements is bell-shaped, then the sampling distribution is approximately normal. And if the population is not bell-shaped, you must measure a large random sample, and it's best to have a sample size bigger than 30. When a population of observations is bell-shaped and/or a large random sample is taken, we define the sampling distribution of mean mu and standard deviation sigma. Suppose x bar is the sample mean. Then the mean of this sampling distribution is mu. The standard deviation of x bar is sigma over root n. And the standard error is s over root n, where s is equal to the sample standard deviation. And remember that standard error is going to be used to estimate standard deviation in the next chapters we discuss. So how is the standard deviation sigma different from the standard deviation of the sample mean's standard deviation of x bar? So let's actually consider a particular example. Suppose our random variable x is the weights of women in the US or something like that. And then sigma describes how individual weights vary. Whereas the standard deviation of x bar, which is sigma over root n, describes how the average weights will vary. In a sample of size n. So one is talking about individuals, one is talking about averages of groups of a specific size. That's the difference here. So suppose we have a hypothetical weight loss clinic, and the population mean and standard deviation of weight losses at that clinic were 8 pounds for the mean and 5 pounds for the standard deviation. So suppose we're taking random samples of 25. Find the mean and standard deviation of the sampling distribution of x bar, and then use the empirical rule to determine intervals that will contain about 68%, 95%, and 9.7% of all the sample means given that sample size. So first of all, the mean of the sampling distribution is mu, which is 8. And the standard deviation of x bar is sigma over root n, which is 5 over root 25, or 1. Okay, so if we repeatedly found samples of 25 and found the average weight loss, 68% of the time we'll have x bar will fall in the interval that is 8 plus or minus 1, or 7 to 9. So if we repeatedly do this experiment, 68% we're going to see an average weight loss between 7 and 9 pounds. 95% of the time, x bar will be in 8 plus or minus 2 standard deviations, or 6 to 10, which says in 95% of our samples of 25, we'll see an average weight loss between 6 and 10 pounds. And 99.7% of the time, we'll see x bar in 8 plus or minus 3 times 1, which is 5 to 11. So repeat part A using sample sizes of n equals 100. What happens to your intervals? So first of all, the mean is still mu, that remains unchanged, which is 8. The standard deviation will be different though. Standard deviation of x bar is sigma over root n, which is 5 over root 100. That's 5 over 10 or 0.5. Okay, now this time we'll have 68% of our samples of size 100. The means will fall in the interval 8 plus or minus 1/2 times 1, which is 7.5 to 8.5. 95% of the time, x bar will fall into the interval 8 plus or minus 2 times the standard deviation, or 7 to 9. And 99.7% of the time, x bar will fall in the interval 8 plus or minus 3 standard deviations, or 6.5 to 9.5. And notice that increasing the sample size decreased the width of the intervals, so the intervals narrowed. This decreases the variability of x bar. Draw a sketch of these sampling distributions of potential means for samples of 25 and 100. So these are bell-shaped curves, and as their probability distribution functions, the area underneath these curves is 1. So this is not an extremely precise picture, but here's the basic idea. Well, first we'll do the one for part A, then we'll do part B. So in both cases, the mean is mu, which is 8. And most of the area under the curve falls within 3 standard deviations of this mean. So 8, 7, 6, 5, because our first standard deviation was 1, 9, 10, 11. So our first curve, almost all of that area falls in there, and it's symmetric about this 8. Now with our next curve, notice that our standard deviation was 1/2, so there's 7.5, 7, 8.5, 9, 9.5. So that curve also has area underneath at 1, but it's decreased down to having almost no area by this value. So this forces this curve to be taller, because this is also a probability distribution function, and it also has to have area underneath it being 1. So this is the n equals 100 group. This is the n equals 25 group. And two things to notice: that as your sample size increases, the variability decreases, which forces things to fall closer to the mean, and the curve gets taller, meaning that falling close to that mean has more area and is more likely. So small planes can't fly well if the payload, which is the combined people, luggage, and fuel, weighs too much. Suppose that an airline runs a commuter flight that holds 40 people. The airline knows the weights of passengers plus luggage for typical customers on this flight is approximately normal, and has a mean of 210 pounds and a standard deviation of 25. So draw a picture of this distribution. So our center value is 210, and most customers will fall within plus or minus 3 standard deviations. So going up, that's 235, 260, and 285. Going down, that's 185, 160, and 135. And the total area of this curve would be 1, but the point is it's bell-shaped and decreases down to 0 at those ends. And this describes the variability in passengers. Variability in individual passengers. Now, if we talk about samples of 40, which is what would be on a regular flight, let's find the mean and standard deviation for our samples of 40. So the mean is mu, which is still equal to 210. The standard deviation of the average passenger weight plus luggage is sigma over root n, which is 25 over root 40, or 3.95. And notice that 68% of our means will fall within 210 plus or minus 3.95, which is 206.05, excuse me, to 213.95. 95% of the time, our X bar will fall within 210 plus or minus 2 standard deviations, which is 202.1 to 217.9. And 99.7% of the time, X bar will fall within 210 plus or minus 3 times 3.95, which is 198.15 to 221.85. So draw a picture superimposing the distributions from A and B. Okay, so for A, we have to have a rather wide range. So 210 is the middle, or the mean for both of them. Then we have 185, 160, 135. On the upper end, 235, 260, and 285. Let's do the one from part B first. So the sampling distribution of the sample mean will have mean 210. I'm just going to draw a line to make myself easier to do symmetry. This is decreased to 0 by 198.5, which is about 200. That's somewhere right here. On the other end, it's 221, which is somewhere up here. So pretty much all of that curve falls within, those are the 3 standard deviations. So it goes down real fast compared to the other one, which is all spread out and will look something like this. The reason that this curve is so flat compared to the other one is that they should both have area 1 underneath them. I'm not sure if I was actually able to achieve that, but the point is that the sampling distribution is the tall one versus the distribution of individual values. So you can expect individual customers to vary, but in your samples of 40, that variation is going to level out. And here's a really useful thing you can do with this. So we're going to assume the customers on any particular flight are similar to a random sample, and if the total weight of the passengers and their luggage should not exceed 8,800 pounds, what is the probability that a sold-out flight of 40 people and their luggage will not exceed its weight limit? Well, if the total weight is 8800. The average weight is 8,800 divided by 40, which comes out to be 220. So we want to find the probability that our X bar is bigger than or equal to 220. And we actually use z-values here. Find the z-value, which is going to be X bar minus mu over the standard deviation of X bar. So that's 220 minus the mean, which is 210, over our standard deviation, which was 3.95. That comes out to be 2.53. So the probability that Z is bigger than or equal to 2.53. Well, to use our Z table, we have to do this whole complementing thing, make this 1 minus the probability that Z is less than or equal to 2.53. Which is 1 minus 0.9943 or 0.0057. So it's quite unlikely that this luggage will exceed that weight, but it's a half a percent approximately, a little bit more, so maybe that's a bit too high. It's up to the airline to decide that. Next, we have the sampling distribution for the sample mean of paired differences. So the first question is, what are some examples of questions that can be answered using paired differences? So one would be, does the Atkins diet lead to weight loss? What is the average age difference between husband and wives? The point here is that really there should be some obvious pairing of your data. Before and after measurement, husband, wife, brother, sister, brother, brother, something like that, where somehow it's obvious that one person is paired with another. So explain which parameter is being described in each of the following situations. Mean, which is just one population mean. Mu sub d, which is the paired difference. Or mu1 minus mu2, which is two sample means. So the difference in the mean number of push-ups new male and new female recruits can do. Well, is there any obvious pairing between male recruits and female recruits? So I don't think so. So this is two different populations. i.e. we have mu1 minus mu2. The mean change in the number of push-ups female recruits can do at the end of basic training compared with the number at the beginning. This is obviously a paired measurement because we have a number before and a number after. In which case we're talking about mu sub d when there's an obvious paired difference going on. Now, the mean of paired differences is pretty analogous to the case of one mean, except the measurements are differences. For example, what I mean by this is you collect your before and after data, find the differences, and then you do all of the stuff with them. So we use slightly different notation to make it clear we're talking about paired differences. So the difference in two measurements for an individual is called d sub I. So you do measurement 1 minus measurement 2. The mean for the population of differences, if all possible pairs could be measured, is mu sub d. This is the true value. The standard deviation of these differences is sigma sub d, also true value. When you move on to your sample, you use the bar notation. Just instead of x, it's d. And the standard deviation, this is the sample standard deviation, is s sub d. The conditions for normalcy are the same. The populations of differences needs to be bell-shaped, and a random sample of any size is measured. And also, if it's not bell-shaped, you must measure a large size, and that is bigger than or equal to 30. And the sampling distribution of d bar is much like x bar. The mean is still mu, it's just mu sub d. The standard deviation, instead of being sigma over root n, is sigma sub d over root n. And similarly, the standard error, which is SE of d bar, is just s sub d over root n. Other than that, there's no difference. The difference really is in the pre-processing, where you find the before minus after, and then you do everything. So here's a question we can talk about with differences. So many of you probably have heard of the freshman 15, or the idea that freshmen gain 15 pounds during their first year. There might be reasons for this other than what they typically say, which is overeating, but here's we're going to sort of address this question and examine whether or not this seems plausible. So in an earlier example, the question of whether students really gain weight on average during their first year of college was posed. A sample that measured 60 students for 12 weeks found the mean weight gain was 4.2 pounds. So is it likely that the mean weight gain for a random sample of 60 students would be as high as 4.2 pounds if there is no average weight gain at all in the population of all students? So to answer this question, we need to know what to expect the sample mean d bar to be for a sample of 60 individuals if the population mean is really 0. We do have to make an assumption that the standard deviation of weight gain is 7. So that thing we just assume we know. So if we assume no weight gain, that implies that the mean, which is equal to mu sub d, is equal to 0. If n is equal to 60, how are our samples going to vary? Well, let's find the standard deviation of d bar. That's sigma sub d over root n, which is 7 over root 60, or 0.904. And using this, we can use our empirical rule to find intervals that would contain our mean most of the time. So we would expect 68% of samples with d bar in 0 plus or minus 0.904, or negative 0.904 to 0.904, meaning some people actually would have lost weight. We'd expect 95% of samples with d bar in 0 plus or minus 2 times 0.904, or negative 1.808 to positive 1.808. And almost all of our samples, 99.7%, would have d bar in 0 plus or minus 3 times 0.904, or negative 2.712 to 2.712. So this means that the d bar we observed, which was 4.2, falls in the top 0.15%. really probably even more top than that. But anyhow, even falling the top 0.15% is really unusual. Suggesting weight gain is real. Now, note, this suggests that there is weight gain, but not that it's 15 pounds. Maybe the freshman 15 is a catchy thing to say, but maybe it's really the freshman 5. So Horn, Reiner, and Barrett describe a study in which 12 men took a simulated driving test after drinking alcohol at lunch, getting too little sleep, neither, or both. Each of the men took the test under all 4 conditions. One of the measurements taken under each condition was the number of times the driver drifted out of his lane during the 2-hour test. For this problem, we're going to consider the mean difference in the number of lane drifts between the condition with alcohol but sleep, so alcohol but sleep, and the condition with no alcohol but too little sleep. That's kind of comparing how do alcohol and lack of sleep compare to each other in terms of impaired driving. So first, define the parameter of interest. So the first thing to notice is that everyone took the test under all the conditions, so you have paired measurements. You have number of lane drifts for each person with alcohol and number of lane drifts for each person with too little sleep. So the parameter of interest is mu sub d, which is the difference in the number of lane drifts with alcohol and number of lane drifts with too little sleep. Describe the sample statistic. So D bar is the mean difference in the number of lane drifts under the 2 conditions. For the 12 men in the sample. So given that the sample size is only 12, describe what is required so that the sampling distribution for the sample statistic described in Part B will be approximately normal. And what we must require, since our sample size is not large enough, is that the underlying distribution must be normal. So the underlying population of differences must be normal. Suppose that getting too little sleep and drinking alcohol at lunch have the same effect on the mean number of lane drifts in the 2-hour period, and the standard deviation for the population differences is 5. Describe the sampling distribution of the statistic you gave in Part B, assuming the situation you described in Part C holds. So if these things have the same effect, then we know that the differences are going to be 0. And the standard deviation of d bar is sigma sub d over root n. And we were told that sigma sub d is 5. Our sample size is 12. So the standard deviation of d bar will be about 1.44.